So welcome to the introduction for the computational neuroscience course Neurodynamics. So I'll first talk a little bit about what this embodied cognition notion is that we'll be talking about. Some of you, I know the ones from the cognitive science program, I think already heard something about embodiment or will hear a lot about embodiment. I'm talking about this maybe in a more specific way, and the way is also not perhaps entirely consensual. It starts out from what I call cognition in the wild. Here, I always show this picture of my kids when they were young. Now they're adults and have their own families. They playing soccer, and I'm going to make a couple of points about that. So one point about that is that entails a lot of cognition, and in fact, pretty much everything that we do in cognition shows up in a context like that, and that the fact that that cognition is involved in action and perception like that actually has consequences for how cognition is done. So let me take you through that a little bit. So first here, let's just look what happens when you do something like that. What kind of mental processes play a role in physical processes? And here's a list here on the left. There are, there's intention. Of course, the game, both of these kids are looking at the ball, so they control their gaze. But as you know, there's also attention outside gaze, covert attention, where they might be monitoring the scene. They do that in an active way. That is, they're looking at particular things, at the ball, maybe at the other player, maybe at the goal, and so on. And to control their perception, to control where they're looking, what they're attending to, they will be using working memory, because you can't make a visual search for the goal every time you look around, right? You are looking already in the right direction, where in your work memory you know, or even in long-term memory, you might know where the goal is, or where whatever else is another player is, perhaps. To make that reasonably efficient. And that is actually already a quite advanced form of representation, because that working memory is not in terms of where on your retina it is, not even perhaps relative to your body frame, because you might have rotated in the meantime or displaced yourself. It might be a memory that is anchored in the world, and that might mean that you're tracking all the time where you are in the world, how you're rotated against the world. Not in some absolute sense, it might maybe relative to some landmarks that you also keep tracking. So you're actually using a little cognitive map that you're updating all the time just to orient on that soccer field. Soccer is a good example, because in soccer you do have attention requirements on the ball and the running that make that you really need to take care of that map. You cannot actually just stop and look around to see where you are currently positioned. And then, of course, you have plans, you have decisions, you do sequences of acts. So decisions, even just where to look, but where to orient, what kind of action to do, when to run, how fast to run, and so motor decisions. Plans, my kids didn't have a big strategic soccer plan, but at least there are a couple of maneuvers, maybe running through the ball and then pushing the ball somewhere else. These things are planned. It's a problem very well described in theoretical computer science terms, but not very well understood in neural terms. It will be a topic for us. Overall, this behavior is goal-oriented. My kids probably didn't have very grandiose goals, but in general, the decisions are biased by things they want to achieve. And of course, then there is the motor control, actually bring about the movement, locomoting. You might be aware that there are pretty good chess computers in the meantime that beat world champions. But if you ever looked at robot soccer, then you're quite aware that they are very bad with motor control. Robot soccer really sucks. Did I already say soccer? I meant robot soccer, I meant. Robot soccer is not very exciting, and a good part of that is because the motor control is very bad. And so motor control here might mean to locomote effectively on an uneven terrain that you haven't modeled perfectly, that is maybe slippery, maybe in part yields to any force to transmit. In this rough soccer field, you might be even sink in. You hit a ball that is a very old ball they have here that might be uneven, maybe has different viscosity or elasticity from different sides. So quite complex problems that kids will solve to some extent, and much better than we technically achieve so far. So there is a lot of cognition in there too. For instance, learning, adaptation, adjusting to changing conditions. When the field is wet or the ball is heavier and so on, you will be adjusting to that. So you will always be learning from experience. You cannot actually prevent yourself from learning from experience. You always get better on all dimensions, on the motor control, the perceptual side, the planning, the strategy, and so on. And there's a lot of so-called background knowledge. The core problem of artificial intelligence here. Background knowledge, and naively would be perhaps the rules of the game. My kids actually didn't play soccer in a very formal way, so the rules of the soccer game themselves were perhaps not so important. But to have an understanding of what the goal of soccer is of course important, and they somehow acquired that. And then there's a lot more subtle background knowledge that is still a difficult problem to understand how that is acquired. So, for instance, that how slippery the surface is, or how fast should you try to accelerate, or how hard should you hit the ball, or how hard can you tackle someone in soccer, even if it's your sister, or things about how the world works, what will happen if you shoot against a piece of glass, for instance, like maybe you don't want to hit the window with the ball, and so on. So there's a lot of knowledge of that kind. I'm articulating that knowledge. When I can articulate it, it's already what we call intentional. It's really about propositional. We can formulate it, but in many other cases, it might be something that is difficult to articulate. It's, for instance, skills that you have, some of which you might have even as a very young child, and they make it possible to bring about this action. So when I emphasize this background knowledge, because that's a core problem of classical cognition, how to get world knowledge into artificial intelligence systems, for instance, and that's contained in something like soccer playing. So it's actually difficult to think of things that are not cognitive processes that are not engaged in soccer. I didn't list all of them here, but they're possibly there. For instance, there's even communication. Actually, my kids, you see my daughter here on the right isn't heading really for the ball. It's more a game of letting someone reach the ball or not. There is actually communication, information sharing, role, turn taking in a situation like that. So there's some social cognition in a situation like that, all the way to language. You might even be talking about the ball, or shouting out, get me the ball, or whatever it is, or watch for the other player. So it possibly contains everything that about cognition might be contained in a play situation like that. It's not by chance. Play is actually probably a way how the development of cognition advances early in childhood. So the fact that there is a lot of cognition in a sensory motor context has some implications, because what that says is that these kind of cognitive processes must be capable of linking to these sensory motor things, which certainly means that they could happen in real time. They will unfold in continuous time. They can connect to states, to graded things like, how hard to hit or how fast to run are continuous or graded variables, and not just categorical. They can be linked to the sensory and motor surfaces, the sensory and motor processes, continuously, perhaps sometimes when you track something, or at least intermittently, that you can connect and then reconnect and so on. And so when you think of cognition as having these properties, then you might reframe that the way we often think about cognition as being about discrete events or decisions, when you make an utterance or react to a stimulus, or when you react categorically, when you say yes or no, or decide something is of a certain kind, that those things are actually not necessarily the given things. Those are the things that need to emerge from the space-time continuous experience. And the most important point for us is that these cognitive processes must be capable of operating in closed loop. And what closed loop means is that the processes that you will be using to propel this behavior depend on the outcomes of of their own action. So closed loop means that as you're acting, your perceptual information changes, and that changes your action. So in motor control, that's what's usually called feedback or control, but that happens also at this level of decisions. Once you hit the ball, and the ball will move in a certain way, and it will depend on that whether the next decision will be to hit it again, or the next decision is to, I don't know, run around your opponent and hit it from another side. And so this capacity to engage cognitive processes in closed loop has important implications. So for those who know anything about control, they know that whenever there's a closed loop system, you need stability. So stability ultimately means that you're reacting to small changes in a graded way so that you stay close to the solution that you had. I'll formalize that much more during the course. It's a very important concept in the course. And so that already has to do with gradedness and time continuous change of some kind of state variables that will say where you are in the continuum of possible behaviors or even possible thoughts. And I'll argue during this course, I'll argue that the loop does not always have to be closed through the world. It can actually be closed within a nervous system, within your network in the form of recurrence. And we'll get to that. So that's a view of embodiment where you say, well, the fact that we do sensory motor like cognition, and that there all kinds of cognition enter into sensory motor conditions, that says there is something like embodied cognition. That's an important phenomenon. So cognition that happens in close relation to a body that acts and that perceives. But the more radical hypothesis, which is not embraced by everyone, is that perhaps all cognition is like that. Perhaps even though it is true that you can just lie in the dark and have thoughts, perhaps the way that is done is not actually any different from the way it is done when you are using your body and perceiving your environment. There are a couple of arguments. I don't want to go through those in detail, but there is certainly one way to put that is to say we haven't discovered any particular boundary up to which cognition is embodied, sensory motor based, and beyond which it's just abstract, computational, symbolic. You see that in the nervous system. If you look at the primary sensory and motor areas, and then you look at the areas associated with higher cognition, like some of the frontal brain circuits, they are very, very similar. There is no qualitative difference. They have very similar kinds of organizations, these layered, homogeneous neural networks that are spread in a continuous way across cortical layers. And similar arguments can be made for some subcortical structures. It's also true in terms of behavioral characteristics, and we'll be seeing some of that, for instance, the kinds of dependencies of things like reaction time or the rate at which you make mistakes in sensory motor kind of tasks versus in more abstract tasks have very similar properties. And I'll talk a little bit about that in the course. And ultimately from theory, we can also say the same kinds of theoretical models explain sensory motor behavior as explains some of the more abstract kind of cognitive behaviors. And the course will actually aim in the end to go to what we call higher cognition. It's still not awfully high because we still want to always link it back to real perception and action. But we can see how the processes emerging from a perspective like that can approach aspects of cognition that we consider higher. For instance, thinking about relations, thinking about verbs, transformations, and doing inference on such things, mental maps. We'll talk about things like that. So the radical embodiment hypothesis would be say cognition perhaps shares these properties of embodied cognition all the way through. It's all done in the same style, even though it doesn't always engage the body, it has the capacity to do it, and therefore is organized similarly, using or respecting the same principles as the more embodied form of cognition. And I am a proponent of that strong form of the embodiment hypothesis. And I'll be taking that perspective here in this course. Here I wanted to make this a little bit more concrete, this notion of a closed loop implying dynamical systems. You don't perhaps know yet exactly what dynamical systems is, and my first tutorial will be about that. I'm illustrating here two forms of that. So one form is, I'll elaborate in the next week's lecture, what we call the Breitenberg vehicle. So this is supposed to be an agent that has sensors and motors, and it orients in the world to particular sources. And what we'll be discussing then is that the movement of a vehicle like that can be described by a dynamical system that has a physical variable, this heading direction where the vehicle is oriented at any moment in time, and its rate of change. So the turning rate of the vehicle is the rate of change of heading. If it's heading somewhere, right, and the road speed with which you change the heading, that's the turning rate. And if the rate of change of a particular variable is a function of that variable, like this black line here, that's a dynamical system. And we'll elaborate on that. And then there are these particular solutions, like an attractor solution here will be going to this source and not going to the other source. And I'll explain that in the tutorial coming. And so here, the closed loop aspect is that as the robot turns, it gets different sensory information about the sources, and you can understand how in that closed loop it could converge on moving to that source and then ignore that source, while if it had turned to that source, for instance, the sensory information from that source will play less and less a role as it is converging on this one. It could have also done the opposite decision. So here it's sort of the physical state of the agent in the world that represents the state that then leads to some kind of closed loop convergence to something. That's the stability, this convergence. But you could also imagine that the same vehicle would be, confronted with these two sources, and now it just mentally selects one of those sources. Let's say mentally it selects the left one, like in covert attention, it will say that's the one that I will pay attention to. I'm looking when, I don't know, the light turns red, and then I will turn. And a way to do that would, then the physical situation doesn't change before and after the decision. So you can't really express the fact that it has committed to a particular decision by its physical state in the world. But you could imagine that the agent has some complex nervous system. I've put a few arrows in here just to suggest that there could be maybe competition and some form of excitation. And perhaps we'll argue that the nervous system could be organized such that some inner variable, which we'll call activation variable, you could think of the firing of neurons as being a representation of being the support for that, represents mental choices. Like if you have an activation variable for every possible heading direction, that will be a neural field that will be defining a couple of lectures down. Then in that field, a peak of activation that is centered over a source of input that corresponds to the left node source versus a source of input that corresponds to the right source, would represent the mental decision that you are paying attention to the left source, not to the right source. Like it's a little bit input on the right, but it's just not enough to sway the field to generate a peak there. So that will be a way of how now the activity pattern in this neural ensemble that we call a neural field would represent that choice of going for the left source without that necessarily being manifest in the physical state of the agent. And typically, of course, both would happen at the same time. That would be really embodied cognition. This would be the more, disembodied form of cognition. And the argument I was just making is that these kind of neural networks that can achieve such things are exactly the ones that can actually also drive behavior and have the properties of that. So that will be a theme. So we'll be primarily talking about these things which we call neurodynamics, where the state is some inner activation representation of a neural network. We will link to behavioral dynamics a couple of times, but that is not very prominent in the course. It's just a sort of a link to another field. So this is the field where biological cybernetics and like cognitive agents, and a couple of other approaches are stronger. In the summer semester, I review this a little bit more detail. We'll do a little bit of that, but we'll focus very much on what we call neurodynamics. So neurodynamics, I'll, of course, lecture really extensively about. There were a couple of lectures that systematically introduced to you that. Pretty much up to Christmas, we'll be really focusing on developing systematically what that is. So roughly speaking, I'll give you now 2-slide summary of that, but I'll elaborate it then over the first part of the course. Neurodynamics is a particular perspective on neural networks. So I'm assuming you all know roughly the notion of a neural network in the mathematical idealization of neurons. Neurons are sort of input-output elements. You have a couple of input variables and an output variable, and the function of the neuron is to sum the inputs. The sigma is a sum. Apply a threshold function, which is usually thought to be like a sigmoid, some function that is 0 for sufficiently negative argument and converges to some constant, often chosen to be 1 for sufficiently large argument, and somewhere in between it transitions more or less steeply from 0 to 1. So that's a sigmoid nonlinearity, the threshold function. So whenever inputs are larger than 0, here the threshold is chosen at 0 in this graph. The output will be non-zero, will be 1, let's say, and when it's below that threshold, it will be 0. So that's a very drastic simplification of what neurons do, and that underlies connectionism, neural network thinking. And if you then think that the output of a neuron could be the input to some other neuron, you can chain them up in this form to form neural networks. This would be a feed-forward neural network in the sense there's a unique direction of how inputs generate outputs, and then those again show up as inputs. So there are no loops. It all just goes in one direction. It's a forward mapping. And a lot of neural network thinking is of that kind. When you think of neural networks as that kind, you can treat the whole system as an input-output system. That is, the output, let's say the sigmoid function output of this last neuron is a function of these various inputs through these intermediate stages. And you can describe the whole thing as functions, function calling, function approximation, and so on. So that doesn't involve time. So you just apply an input and get an output. In physical neural networks, it might take some time for the answer to be provided, but that is just some kind of delay. It's not something that evolves in time in some independent way. It's different when you have what is called recurrency. Recurrency would mean that some of the outputs also serve as inputs. So, excuse me. Well, here's the simplest possible recurrent network of a single neuron that just, for instance, self-excites, so its output is part of its input. That's no longer, it's no longer possible to think of that as a input-output device because you don't know some of the inputs because those depend on the outputs. And so the solution of how to solve that implicit equation is to think of the outputs as being previous outputs. In some previous time step, you provide an output. That input, that output serves as inputs in the next time step. And in the next time step, and will determine the output the next time step. So you will see some connections networks actually really do it that way, introduce some iteration with some discrete time. Of course, in real neural networks, there isn't like a central clock that updates inputs and outputs this way. Of course, real neural networks spike, and you might think, the spikes may be something like that. They are not. They are not on a grid of discrete times. They are what we call asynchronous. So really, we have to think of the spikes as just approximating some time continuous thing. That's the picture we'll be taking. I can elaborate on that later. And once you do that, you need really time continuous variables. So we'll talk about activation as a representation of the inner state of a neuron, and it could be physically something like the membrane potential, the spike rate. And that activation state evolves continuously in time, and it will turn out that it's differential equations of this kind, where the dot is the rate of change of activation, and on the right you have activation itself and any inputs. And here, for instance, a input from that same neuron, the sigmoided value of that same neuron. That would be, technically speaking, what we call neural dynamics, and models that combine a lot of differential equations like that will be neurodynamic architectures. That is the language in which we'll be speaking about in this course, and I will elaborate that much more over the next couple of lectures. So we do this also in the second abstraction, not just continuous time, but also continuous space. So neural networks have these discrete neurons that are countable variables and have indices, but in many cases, actually, this doesn't make too much functional sense. There are a couple of arguments for that, and I'll go through some of them. Certainly, if you think of how neural networks generate behavior, there are actually no single effects in psychophysics where you would see the discrete nature of neurons, where you see, now, another neuron came in and therefore the behavior changed in some step fashion. That's not the case. The behavior actually changes continuously, and one can theoretically understand how that comes about. It runs under the label of population code, and I'll have an opportunity to talk about that. Where, for instance, if you can make a population code with just 2 neurons, if these 2 neurons vote for behavior and the vote depends continuously on their activation level, then the activation level determines the behavior, and that varies, let's say, continuously. And then the fact that they're 2 neurons doesn't really matter. And so the way we formalize that is that we smear out many neurons that stand for different things. That means they get different inputs or they project different outputs. And the way we think of that is that these activation variables, we call them then activation fields, are defined over some continuous dimensions that are defined either in terms of sensory input, ultimately from the sensory surface. So for instance, it could be retinal position, or it could be some feature value like color or orientation or movement direction and things like that. And so the connectivity from a sensor to the field would set up these dimensions, and then would have continuously many different activation states. So these would be things that some of you might have known as neural maps, like topographic maps in cortex, visual cortex, or auditory cortex, and so on. Or this is similar for motor systems. So motor system, you might have a continuous ensemble of neurons that will represent by a neural field, and they project onto the motor system. When you think of motor systems, they are actually always dynamical systems in this behavioral sense. For instance, just even through the the peripheral reflex loops. At the very end of the course, I will perhaps illustrate that idea. We talk about that also in the winter semester, in the summer semester course. So these dimensions can also be defined by the connectivity on the output side, and I'll elaborate on that a little later. So very important in over the course in the examples I will be discussing is this notion of interaction, and that so interaction is essentially some regular pattern of recurrent connectivity in these continuous neural networks that we call fields. So for instance, neighboring locations would typically be considered to be excitatory to each other, drive activation up. That makes peaks stable against decay. Locations in the field that are further removed from each other tend to inhibit each other. So that promotes essentially selection. So it prevents a peak from just spreading. If you had only this excitation, it would always excite the neighbors. The peak would grow laterally, and we'll have an opportunity to look at that. And introducing this kind of inhibition stabilizes peaks against that kind of diffusion. And it's important for things like selection decisions and sequences and things like that. So that will be the core technique that will be capturing under the label of dynamic fields, dynamical field theory. Yeah, so the course essentially illustrates, first of all, introduces the concepts and then illustrates results from a theoretical research program that is my personal research program and of a whole community. It has a long tradition. It's a research program in which we try to get to develop a theory of both behavior in the sense of motor behavior, acting in the world, and thinking when you don't act in the world immediately, but a theory that emphasizes this link to the sensory motor domain, emergence also in the sense in evolution and in development, thinking emerged from sensory motor behavior and became, in a sense of creating the invariances that you observe at the level of cognition. And that means that the theory is, we talk about neural process accounts. That is, in the theory, we really describe the processes in a way that they could actually be enacted, like you could even put it on a robot, but in a way that is consistent with how nervous systems do that. So for instance, not postulating that you would have a CPU that you can send some message to or store information somewhere. You would all ultimately be able to do all of this just by neurons sharing activation through some connectivity pattern. That will be ultimately the currency in which all of this is done. That's what I call neural principles. I'll be more precise about that set of principles. And a third aspect of this research program is that we'll be aiming at understanding elementary forms of cognition and of behavior, but try to embed that or see how those are primitives or elements for naturalistic tasks, for tasks you actually achieve, like the tasks that I talked about in soccer playing. Will of course not really model soccer playing, but will model tasks that you can see embedded in a naturalistic task like that. And sometimes take this metaphor that some of the more classical approaches to cognition are strongly driven by the idea of information that you process and then make a decision. So it's a feed-forward input-output kind of calculation. Input the information, output your answer. And in a way, if you think about the embodiment situation, that's sort of like modeling cognition as the penalty shooting, right? The player stands, stimulus comes, the ball, and then you decides jump left or right. And it is interesting perhaps to embed that in a picture where it's actually a continuous process, where the penalty shooting is just a very special situation out of a more general situation where the behavior already influences the kind of perception information you get, closed loop, and where you're continuously making decisions, and where the discrete event of you making a decision like that emerges from continuous behavior like that. So that's what I mean by naturalistic tasks. It's also an empirical research program. That is, it's important, of course, to support theoretical ideas like that by looking for experimental signatures, behavioral signatures, ultimately, sometimes neural signatures of these postulated principles. And I'll show you a limited number of examples like that, where we can take some qualitative, some quality of behavior and that can be measured quantitatively, and try to link that to fundamental principles in the theory. So it's not just a question of modeling, modeling data, fitting data. It's really a question of ultimately finding some constraints, some kind of law-based account for properties of such embodied cognitive systems. Yeah, and then there's a third aspect to this research program, which is to make generative models, to be able to actually produce behavior that has these cognitive properties. We do that often in robots. It's less as part of actual robotics, which has its own concepts and criteria for what's successful, driven by other constraints. But we're using the autonomous robots as demonstrations that, based on the sensor information that we model and that we derive directly, let's say, from cameras, even this little robot has cameras here, how we can drive behavior from these sources of sensor information and autonomously organize sequences of actions that lead to goals. And so we, in our research, we very often try to do that. And what that provides as sources of evidence is that to put together into an integrated system that these systems actually really are capable of generating the behavior. These robots are, of course, not really driven by neurons. We simulate these neurons on computers, even though there are some colleagues of ours, I'm just working with a team of those on a new grant proposal, who are actually building neuromorphic hardware, who are building chips that are neuron-like, and they really implement some of these things directly on those chips. I'll not be talking about this in this course. This entails a lot of additional layers of complication. But the notion is that the fact that it's implemented in some way on a technical system rather than on a biological system is not supposed to matter. That is, we're not taking any advantage of particular entries into the technical system. We're really trying to do what would be required to do this in an organism, and then we can see, demonstrate, for instance, that it's possible to generate behavior. Sometimes we're able to also point out that that there are certain aspects that are not well understood. For instance, when there's a hole in your argument, something doesn't work, you're missing a piece. Sometimes you're finding out that a piece that everyone argues must be there isn't actually necessary. You can generate behavior without that piece. For instance, without a symbol, you can make something that looks like reasoning and don't have any symbolic representation. That's an interesting insight, that it's not necessary to have symbolic representations for certain tasks. So I'll allude to that research program occasionally in this course. I'll use a couple pointers to that. So the last thing I want to do in this introduction is to tell you a little bit about what you're supposed to learn. And this course is supposed to be fun. You're supposed to learn about new stuff that you don't know yet, wildly interdisciplinary, from psychology, cognitive science, neuroscience, robotics, artificial intelligence, you name it, and even like physics and neurodynamical systems, so on. So more specifically, we'll be talking about contents. So there's the contents of embedded cognition, what I just outlined, and specifically detection, selection decisions, working memory, and memory. The memory is a form of long-term memory. Will be concrete technical things you will be learning. We'll be talking about these specific theoretical ideas: behavioral dynamics, neurodynamics, dynamic neural fields, dynamic field theory. In the end, you will know that ad nauseam. You'll learn something about some, let's say, the conceptual foundations of what neural principles of the function of neural networks apply. So you know what rate code is, what neural maps is, what population code is. You will know a little bit about neurophysics, not in detail, but the fact that neurons have synapses and spike, and you'll know some of that. And you will know a little bit about the underlying mathematics. So we'll certainly then be able to tell me in the exam what a dynamical system is, what makes it special. You'll be able to say what attractors are and instabilities are, and what stability is. You will not have a technical understanding, but you'll know that what it means to numerically solve a differential equation, and be familiar with the fact, this idea that on the computer, you're looking at time courses generated by solving differential equations. Again, this is more concepts. It's not that you will then be able to solve differential equations or write code necessarily to solve them numerically. We'll also show a little bit how this relationship between theory and data works, and what it means to account for behavior in process models. Only a little bit. I mean, the whole entire courses, like mathematical psychology courses, are about that, and so there's just a small aspect of that in the course. And the use of robotic demonstrations and simulations will make use of that. You'll become familiar with that way of doing it. It's not so much about, it's more about a style of establishing evidence than really a very technical kind of knowledge that you have there. Yeah, in terms of skills, I would say the main academic skill is actually less than math and more really the general capacity to relate to scientific writing. Because it's interdisciplinary, it becomes a real conscious effort to try to understand scientific texts when they're not direct developments of the textbooks that you have studied. So reading, understanding scientific texts, and writing scientific technical texts, including use of mathematical concepts, but really explaining them, not just writing down equations, but also reading the text, linking these equations, making sense of them, illustrating such technical ideas, documenting correctly these illustrations, explaining your jargon and so on. That will be a skill. That's one of the real practical skills you learn here. there are particular skills linked to dynamical systems that are quite useful. I mean, even if you know differential equations, here you will not typically solve them, but you will, for instance, mentally simulate them. And that has to do with the inverse problem. I'll explain that more formally next lecture. The inverse problem, that is that you have some kind of idea of what solution you want, and you have to think about what equation would make that solution. That's what, when you design a dynamic systems. Those who have some engineering background might have heard about the design of a control system. That's a much more technical way to do this, but we'll be designing nonlinear dynamical systems, so it's really quite interesting. Again, we'll not do this in a very technical form. We'll do it in intuitive form. And then lastly, there, how to, I call these interdisciplinary skills, and how to handle concepts from a different discipline. That means, first of all, recognizing that they are from a different discipline. They're not just daily life terms, that you have to be aware of the conceptual and intellectual history of that field, and that you have to manage that you don't always know everything about these different areas. When you're working interdisciplinary, you have to have a better understanding of your own discipline, because you need to be aware these are the concepts that we use, and it's not automatic that everyone else uses them in the same way. And then you have to have better metacognition, that is how to handle the various degrees of knowledge you have about different domains. That's a very important skill for everything that you do today as a academically trained, computer science engineer, scientist, whatever. Because essentially the way we use these disciplines out in the real world, if it's in research development or even just in corporations, very often has this feature that you have people with different backgrounds, different skills, different sets of concepts collaborate. It might often be, with business people or across, the disciplines maybe are not the same ones here, but the fact that you have to have this interdisciplinary discourse is very, very common, increasingly constrained, increasingly as the computerization of pretty much all processes brings together very different branches that are all connected by sharing information. That promotes very much that kind of interdisciplinarity. So it's very useful to have that. Yeah, that's about as much as I want to announce about the direction of the course.